Now, I want to give you two other perspectives of this logistic regression. One is the maximum likelihood perspective. The other one is called the log-odd perspective. And these two perspectives, they are useful to give you some intuition of what this logistic function really means. It may not help you too much in terms of computation if you worry about how to make it faster or not. Okay, so let's look at the logistic regression again. So this is your loss function. It's the cross entropy loss. You're trying to find a theta that can minimize this loss function. So I can express my loss function as follows. Then I can do a very simple trick by putting a log on this function. Okay, so what I do is that I put a log on this entire thing. I am able to put a log because log is a monotonically increasing function. And so if I put a log here, I will not change the minimizer. If I put a log here, then the summation becomes a product. And also these products will become a power. Okay, so now you are turning this summation of all these y times log h and then 1 minus y log of 1 minus h terms. You can write them as a log of the product of h to the y and 1 minus h to the power 1 minus y. Okay, so I can further do some calculation, okay, by removing this log function. Okay, so you ask, you put a log here and then you want to remove the log again. Yes, I'm doing this because I want to turn this problem into this particular form. Okay, what is the form that I want? I want to remove the log. If I want to remove the log, I can just turn the mean to the max because I have minus sign here. And so I have this product term. Okay, so when we get to this equation here, this is what? This is a maximum likelihood estimation of certain distribution. And this distribution should be familiar to everyone, is a probability to a number times 1 minus the probability to the power 1 minus some number. And this is exactly the Bernoulli random variable. Okay, so if you remember, the Bernoulli random variable has a likelihood of p to the power yn and 1 minus p to the power 1 minus yn. And if you take the product of n going from 1 to n, that will define the likelihood function of a Bernoulli random variable. Because you flip a coin, okay, you either get 1 or 0. If you get a 1 here, you have a probability p. If you get a tail, you get this part, so you get 1 minus p. Okay, so that is the likelihood function of a Bernoulli random variable. So by looking at this cross entropy loss, effectively, I'm trying to solve a maximum likelihood of a Bernoulli random variable function. Okay, so that gives us some intuition that what I'm trying to do with the logistic regression, there should be some connection with the probability, and the connection with the probability is through this Bernoulli random variable. Okay, so now we ask, what is the underlying probability then? So we can look at this form, and how do you interpret this h as a probability? Well, you can interpret this h as a probability p, so you can replace this by a constant p, but that is not too good. Why? Because p is a constant, it doesn't change with x. So we may want to say, how about we consider p be a function of x as well, meaning that this is a function of xn. So if you only put a constant p here, it doesn't really reflect the reality that the p has to be changing depending on x. So we call it as a probability on xn. But if you look at this function again, this probability of xn, this is really after you have seen the probability of getting xn, right? So it's after you have seen xn, what is the probability of getting class 1 or class 2? And so one way to interpret this h, if you want to use the probability perspective to look at this problem, then one way to do so is to consider your h as this posterior probability. Okay, so you can say that my h can be interpreted as the posterior probability of getting class 1, given that I have a sample xn. And then the probability of 1 minus h, it will be the posterior probability of getting 0, given that you have seen xn, the sample xn. Now, if I use this perspective, then there's something that can be interpreted in this equation. You're finding a theta, a model parameter, that can maximize this Bernoulli process. And then this Bernoulli process has an underlying distribution. It's defined through this posterior events. Okay? And so, and so by solving this problem, you'll be able to really maximize the likelihood of getting that posterior probability. And therefore, your H, okay, so if I give you a new sample X that is not inside this training set, X, and then I ask you, okay, what is the meaning of your H of X? Okay, so basically what I mean is that you have a new sample X. This is your testing data point. I put it into your model. Your model is already trained. It's called a H theta of X. I ask, can you give me an interpretation of this quantity? Then I am able to give you the interpretation as this number will represent the posterior probability of you being class 1. Right? Okay, now this perspective is not given in the linear regression case. The linear regression case will only tell you that this is my testing sample, and then I will give you a score. And the score will be linear. It doesn't give you any probabilistic meaning for the linear regression model. For the logistic regression model, once I have trained the H, you give me a testing data point, I can tell you that your number, your numerical value, okay, it could be 0.99. That 0.99 refers to the posterior probability that you belong to class 1, given that I've seen you. Okay, so that is a lot more interpretable in that sense. Now, the second perspective that I want to bring up is this notion of log-odd perspective. If you're statistics students, you probably have come across this term before. It's called a log-odd. Now, if not, then it's also not too difficult to understand what I mean here. You look at this loss function. This loss function, you have this log of h and then log of h and then 1 minus y and then log of 1 minus h. So you can group the two log functions together because this 1 minus yn times log is log of 1 minus h minus y times log of 1 minus h, right? So you can break this term into two, and then this log and then this log and this log, you can combine them together because they both have the y. Okay, so you can combine the third term with the first term, and since the difference between two logs will give you the ratio, the log of the ratios, so you can have this log of h divided by 1 minus h. This term remains because it comes from the second term. This term, this log of this ratio, is defined as the log odd. Okay, so this function is called a log odd in the statistics literature. It has certain interpretations, which I'm not going to go into details. But if we put this h into here, okay, so what is h? Let me remind you, h is the sigmoid function. It has this form. You take this equation, put it into the log odd, then you can get this log of 1 over something divided by something, and then 1 plus something. It's a very complicated creature, but never mind. We can cancel out the denominator, right? Because the denominator, they are the same. So if you cancel them out, what do you get? Well, you get log of e to the power theta transpose x. And then there's a log outside. And the log will, of course, cancel out with the e. And so you get theta transpose x. Okay? So after doing all these interesting exercise, you find that this log thing is indeed just theta transpose x. All right. So what is the implication? Well, the implication is that this logistic function that you put in, you are actually ensuring that this function is linear in terms of this log odd. Okay. Another implication is the discussion that we are going to look at is the convexity, okay? Because by doing this, you can show the convexity a little bit easier than dealing with two terms, okay? You just need to worry about the last term. The first term, in this loss function, this is still the cross entropy loss. However, by written it as this way, I can show that this cross entropy loss can be written as a linear term plus a log of 1 minus h term. Okay, so that can simplify the expression a little bit. And in addition, it has certain statistical meaning of the loss.